All right, so welcome back to Math 140 Business. We are now in week 10, Tuesday of week 10. I have no idea what lecture it is, but it is, we are in the 10th week, Tuesday, November 2nd. And we are doing today chapter 18 on comparing two proportions. Comparing two proportions. Up until now, we have focused our attention on one proportion. In fact, if you look back at chapter 17 and chapter 16, the confidence intervals, we had a confidence interval for proportions. Let's recap. Let's quickly remind ourselves. So in chapter 16, we had a confidence interval, for one proportion. So let me write that confidence interval for one proportion. And it was p hat plus or minus the square root of p hat 1 minus p hat over n. Don't forget my z star in there. Okay, so that was the confidence interval for one proportion, and that was essentially the entire first chapter 16. And then we also did the +4 confidence interval. And so we also had p twiddle plus or minus z star times the square root of p twiddle 1 minus p twiddle over n. So this is also a confidence interval for one proportion, but this one was the small sample version. And this one here was the large sample version. What's the large sample version? N p hat and n1 minus p hat must both be greater than or equal to 10. And the small sample version, we just require n to be greater than or equal to 10. So a much smaller sample. That was the recap of confidence intervals. That was chapter 16.
Professor, I have a question.
Yes.
What was the difference between p hat and p twiddle?
So p hat is equal to the number of successes divided by the sample size. Someone remind me, what was p twiddle? Oh, and that was also for p twiddle, it was divided by n plus 4. Don't just divide by n. I made that same typo last time before someone caught it. So someone remind me, please, what is p twiddle? Anyone remember?
X plus 2 divided by n plus 4.
X plus 2 divided by n plus 4. So in other words, if the number of successes is x and the sample size is n, then p twiddle is arrived at by adding 2 to x and adding 4 to n.
Thank you.
Okay, so that was recap chapter 16. And then a recap for chapter 17. 17 was on hypothesis testing. And we also did a hypothesis test only for proportion so far, where p is equal to some specific value. And we had 3 alternatives. P is less than that value, p is greater than that value, and p is not equal to that value. Those are the 3 possibilities. And then we had then we use our calculator to find the p-value. Right, you had 3 possibilities. The less than side were over there, The greater than side, we're over there. And the not equal to side, we're on either side. Those are the three situations. And if our value falls into those critical regions, that's when we reject the null hypothesis. So we want to calculate these cutoff values, right? All those cutoff values. Cutoff values. What are the values for which, if our data point is beyond them, we would reject the null hypothesis in favor of the alternative? And the cutoff values is z equals plus or minus, depending on which side you are, p hat minus p naught, which is the assumed value based upon the null hypothesis, divided by p hat, p naught, 1 minus p naught over n. So the plus being on the right and the minus being on the left. And what is the probability of being past that? That was the p-value. So the p-value equals probability of being past the actual value. I could say this, being past z, being past this value z. Right? So z equals this number, this z equals this, how can I illustrate? Okay, so z equals this. We'll do it like that. So p-value equal to probability of being past z equals that number. And if the p-value is less than alpha, reject the null hypothesis. Otherwise, do not reject the null hypothesis. And we did examples of that last time. What we're going to be doing today is just an extension of that to some new situations. There's nothing new theoretically from those basic ideas. What we're going to be doing now is working with two samples. We have two proportions. So on your calculator, which of the possibilities do you think we're going to be using today under the stat tests column that we have not used before?
Two variables.
Not two variable, we're still on stat and tests. Can you scroll for a second? Yeah. Go to stat and tests and then look through the various possibilities. Okay, remember what we're doing today. Chapter 18 is comparing two proportions. So which of these numbers do you think, or which of these situations do you think are going to be the ones that we're working with today if we're going to be comparing two proportions? Anyone?
Would it be two prop z-test?
So we're going to have the two prop z-test. And which of my confidence intervals are we going to be using? We need one for hypothesis testing and we need one for confidence intervals. So the two prop z-test we're going to be using for proportions. And which one do you think we're going to be using for intervals?
Two prop z interval?
The two proportion z interval. Okay. So even if I didn't give you any theory from the book, even if I just straight up said, okay, let's do some problems, we don't even need the theory really to do the problems because the calculator gives us everything we need. And so, and on test, you'll never be asked to do it by hand. Everything's going to be from the calculator. But nevertheless, having the theory is not a bad idea. So now for two proportions. So for two proportions, you're going to have sample one and you're going to have sample two. Sample one is going to have its true value, P1, the true proportion, and sample two is going to have its true value, P2. of course, we don't know those values. If we did, I wouldn't need to take a sample. So we're going to have our P1 hats. This is our sample value. And we're going to have our P2 hats. This is our sample value for the second sample. What else do you think we're going to need from the first sample and the second sample that might be relevant to actually solving the problem? That we're going to need to plug in on our calculators. What are some other things that we might need to plug in?
Sample size.
Sample size. So N1, sample size for the first sample. N2, sample size for the second one. Yes, no? And of course, I might ask for X1, the number of successes in my sample, and X2, the number of successes in my second sample. So we're going to be doing two things. We're going to be doing confidence intervals, and we're also going to be doing hypothesis testing. So let's do the confidence intervals first. Remember what a confidence interval is, right? In general, it's going to be the estimate plus or minus Z star times the standard error. So the first question is, what's our estimate going to be? So when you're comparing two proportions, very rarely do we care about the specific values of the first and the second individually, but rather it's their difference that I care about. Like if I think women are better than men in some area or men better than women, I might take samples of each, compute their values, and it's the difference that I care about. So the value that we're going to start with for the confidence interval is P1 hat minus P2 hat. It's the value, it's a difference between the first sample proportion and the second sample proportion. Now, for one professor, for one, what did I say, professor? For one proportion, I don't know where that came from. Our standard error was P hat 1 minus P hat over N under a square root sign. That's not going to work here because we have two proportions. So which one will we use? So the answer is we do both. P1 hat 1 minus P1 hat over N1 plus P2 hats 1 minus P2 hat over N2. Make sense so far? Again, I'm not giving you the reasons why these formulas are in place because the derivation is beyond the level of the course. I'm just giving you the formulas, the actual confidence interval formulas that we're going to be using. Okay, this is the large sample confidence interval. N1 P1 hats, N1 1 minus P1 hats, N2 P2 hats, and N2 1 minus P2 hats, right? Those are the number of successes for the first trial, number of successes for the second trial, number of failures for the first trial, number of failures for the second trial. In the first case, if you recall back in the previous chapter, each of those numbers had to be what in order to be allowed to use the large sample confidence interval?
Greater than 10.
Greater than or equal to 10, correct?
Yes.
Okay, so we're going to have a similar situation for two samples, but yeah, okay. So for two samples, it's going to be a similar situation. Also, each of them must be greater than or equal to 10. To do that, I can use the large sample confidence interval. What if, though, I don't have that? What if I have a small sample? What if I don't have that situation hold? And I want to go to my small sample confidence interval. what do you think I'm going to replace P1 hat and P2 hat with for the small sample confidence interval?
P twiddle.
P1 twiddle minus
P2 twiddle.
P2 twiddle plus or minus Z star. And then what are these ones going to be?
It's gonna be P twiddle and then parentheses 1 minus P1 twiddle and then divided by n plus 4.
And 1 plus 4. Sorry, and 1 plus 2, because since we're going to get plus 4 overall, but it's going to be 2 in this group and 2 in this group.
Okay.
Okay. And same thing here, P2 twiddle, 1 minus P2 twiddle over N2 plus 2. But this time, because it's 2 in each group, I'm just going to have P1 twiddle be X plus 1 over N plus 2. And the same thing for X1 plus 1 and 1 plus 1, X2 plus 1 over N2 plus 2. So it's the same idea. I'm going to get a total of 4 extra in my sample sizes and a total of 2 extra in my successes. But because I have 2 different ones, it's going to be, I'm going to add 2 for each on the bottom and 1 for each on top for a total of 2 extra on the top and a total of 4 extra on the bottom. Does that make sense?
Yes.
Okay, and in this case, we want N1 and N2 each to be greater than or equal to 5 because we want it to be a total of 10. And the reason I was hesitating for this one is because everything else is split. I was looking for confirmation because, to be honest, I just forgot about whether or not it should be plus 10 there or 5. Because everything else kind of splits and I can't find anything in the book. So we're going to keep it at plus 10 until I can verify one way or the other. This one might end up changing to 5, but I'm pretty sure it's 10. So other than that, are there any questions with the formulas for the different confidence intervals for 2 proportions? So let's do an example then. Let's do 2 examples, one for the large proportion and one for the small proportion. And we'll do it both by hands and on the calculator so we can see that the calculator does in fact give us the right answer. So I'm going to go to the back and pick a question. Okay, here we go. So if we have the book, it's on page 410. It says truthfulness in online profiles. Many teens have posted profiles on a social networking website. A sample survey in 2007 asked a random sample of teens with online profiles if they included false information in their profiles. Of 170 younger teens, so of the younger ones, and these ones were aged 12 to 14, of the 170, so N1 equals 170, 117 said yes. The number of successes were 117. Of the 317 older teens, older being 15 through 17, 152 said yes. So for A, it says, do these samples satisfy the guidelines for the large sample confidence interval? Is the number of successes and the number of failures for each one greater than or equal to 10? Yes, no?
My bad word.
Are the number of successes and the number of failures for each one greater than or equal to 10?
Yes.
Yes. Okay. So yes, all 4 conditions, not conditions, all 4 of the of these guys.
Criterias.
That's a good one. Criteria, that's a good one. All four criterias are met. That's why I don't speak English good. All four criteria are met. So B, give a 95% confidence interval for the difference between the proportions of younger and older teens who include false information in their online profiles. That's it. Give a 95% confidence interval for the difference. So where do we go?
On the calculator?
Calculator. Which one are we gonna press in the calculator? Boom, I already got it. That's how fast it should be. If you know which button to press, you go right there, you put it in, you're done. Which one are we gonna do?
2 prop Z test?
This is not a test. This is an interval. We are doing a confidence interval. Confidence intervals are not tests.
Is it number 9?
It might be. I already pressed it.
Two samples the
The
Two
B, 2 prop interval.
Let's go back and check. It is not the 2 sample, it's the 2 proportion, it's B. The 2 proportion Z interval. And what 5 things do they ask for the 2 proportion Z interval?
X1, N1, X2, N2, C level.
All right, let's put them all in. When we do that, what is our interval that we get? From what number to what number?
Negative 0.32.
Okay, I think you did something wrong.
I might have the wrong number.
I got 0.12001 to 0.29747.
Okay. So what does that mean? That's the confidence interval? What would you conclude based upon this study?
That we are 95% confident that the number that we're looking for lies between these two values.
Okay, so what you just said is correct, but if the problem says, say it in the context of the problem, you would not get a lot of credit because you've missed all references to what's truly going on here as a practical problem.
Mm.
So I don't want just an answer that's generic for confidence intervals. I want specifically for this situation, what do we conclude?
The difference between the younger line and the older line would be between would it be 12% and 29, 30%?
Yeah, so you can always round if you want to live like that. So we are 95% confident that the true difference in proportions between those of the younger crowd and those of the older crowd is somewhere between 12% and 30%. So would you then claim that the younger group lies more often than the older group? Does the data support that argument?
Yes.
Why in particular? What's not in the confidence interval?
Zero.
Zero. If they were the same, the difference should be zero, correct?
Yes.
And zero is not in the confidence interval. So we're 95% confident that the difference is not zero. In other words, that they're not the same, that younger people, teens, whatever, lie more often than older teens. That is the ultimate conclusion.
And is there a possibility to get a negative then? So to prove the other way is true or no?
Sure. I mean, if the confidence interval would be so far to include zero, well, let's try it. Let's do 99%. Because we know that the higher the percentage, we know the wider it's going to be. So let's see what happens if we go to 99%. If I go to 99% and I calculate, still not, okay. So let's go to 99.9%. So 0.999. Still not. Okay, it'll be a while. But basically, the numbers are so far apart that until the confidence was significantly higher, I would conclude that P1 is greater than P2. Does that make sense?
Yes.
So let's do another one. This time, let's do another confidence interval. Let's do the following situation. Example. The Abecedarian project was a randomized controlled study to assess the effects of intensive early childhood education on children who were at high risk based on several socio-demographic indicators. So who cares? No math yet. The project randomly assigned children to a treatment group, which was provided with early educational activities before kindergarten, and the remainder to a control group that I guess didn't do anything. Our recent follow-up study interviewed subjects at age 30 and compared the college graduation rates. Here's the data. You have two populations, two samples, or population 1, population 2. This is the treatment group. This is the control group. The sample size, N, was 52 for those and 49 for those. The number of successes was 12 for those and 3 for those. And we want a 90% confidence interval. And what are we curious about here? We're curious about whether or not the treatments of giving these kids lots of early education software and programs, you know, like what were those? Was all the craze when I was growing up.
ABC야?
Which one?
Do you remember ABC야 or something like that?
No, I'm thinking of the music. You know, like if you play classical music to kids, they're going to be smarter type thing.
Oh, yeah.
Remember those, like music by Einstein or with Einstein or something like that? I don't know. So a lot of parents believe that if you really throw education stuff at your kids when they're like, you know, really, really small, they're going to grow up to be smarter. So we're curious, is P1, the true proportion for the first population, greater than P2? Is the true proportion greater than or not? So we're going to form a confidence interval. So what's our confidence interval going to be? Well, normally it will be P1 hats minus P2 hats, but you'll notice that the number of successes here is not 5, or it's not 10, right? We need 10 of each, correct? The criteria, each of them has to be 10. And we only have 3 successes in the second group. So I can't use the large sample size confidence interval, but instead I will use the small size confidence interval. Oops. P1 minus P1 twiddle minus P2 twiddle plus or minus Z star square root P1 twiddle 1 minus P1 twiddle over N1 plus 2. And then P2 twiddle and 1 minus P2 twiddle over N2 plus 2. Now I did forget in the first one to actually do it by hand. I just forgot. So let's do it for this one. Let's first do it by hand and then we'll do it with a calculator. So first, in this example, what is P1 twiddle equal to?
Be 13 divided by 54.
Excellent. 13 over 54, about 0.241. What is P2 twiddle equal to?
4 divided by 51.
Excellent. 4 divided by 51, which is approximately 0.078. So my confidence interval becomes P1 twiddle minus P2 twiddle. That's 0.162 plus or minus. Let's hold Z star for a second. And then we get P2 twiddle times 1 minus P1 twiddle times P1 minus P1 twiddle. P1 twiddle times 1 minus P1 twiddle divided by 54. And then we're gonna do P2 twiddle times 1 minus P2 twiddle divided by 51. We're then gonna add those two numbers and then square root them. And what do we get after square rooting? I know what I got. I wanna see if you guys got the same thing that I did. That whole radical with square rooting, what do we get? What do we get? Is anyone actually doing it? If not, I'll just say the answer, but if you're still doing it, I'll give you a couple seconds. Is anyone there?
How do you
Hold on,
get
hold on,
the Z
I'm sorry.
critical?
Sorry, I didn't hear, what was that?
How do you get the Z star?
Oh, well, I gave you that. What's a Z star for 90%?
Oh, 0.9.
No.
Oh, it's the thing we got last time. My bad. Let me-
So what's a Z star for 90%?
Isn't it 1 point something? 1 point,
1.645.
I thought it was 1.645.
1.645. It's a fact. 1.645. Right? Remember, 90% confidence interval means we want the inside to be 90%, which means we want 5% on each side. So we want the value that cuts off 5%. So if I go to my calculator and I do normal CDF, or if I do inverse norm, 5% on the right, I get 1.644853626. That is my Z star. But anyway, so what do I get for the middle part? For the whole radical part, what do I get? Is anyone doing it? If not, I'll just give the answer. So let me know.
I'm doing it. 1 second.
Okay.
Yeah, I'm doing it too. It's just kind of slow for me to do it.
Gotta get you guys faster at calculator manipulations.
Is the part that's like just in the radical, is that what you want, or do you want us to add the?
Well, I mean, eventually with the radical too, but if you only have the part inside, I'll always be able to tell you if you're
I
correct.
have it square rooted, but I don't have the Z star and then the other part.
Yeah, just the part past the Z star, just the radical part. What's the-
Oh, 0.0692.
Okay, excellent.
Yeah.
So if I multiply that by 1.645, I get 0.162 plus or minus 0.114. Which gives me,
I don't know if you could do this, but is there any way you could like put the camera towards your calculator so we could see the functions you're doing?
well, I'm just plugging in numbers into these guys and multiplying, dividing, adding, square rooting.
No, but I mean like like in the future, like if we're doing something that needs a formula, could you do it on your calculator? Like show us, like, or no?
Well, I'm just asking, what do you mean? I mean, do you mean like this kind of formula where I'm plugging numbers into there?
Yes.
I can try. I don't know how,
I mean, it's
um,
okay. It's fine. I wanted to know if you could, but I mean,
I mean, I can be a little more specific in what I'm writing out, if that helps. Like, for example, hold on, just died for a second, 1 second. I can do, like here, for example, I can throw in that this is equal to 0.241 minus 0.078 plus or minus 1.645 square root of 0.241, 1 minus point, is this what you mean? Over N1 plus
Well,
2, N1 was,
this is great, but I mean, I'm still trying to figure out my calculator, so I wanted to see if whatever you do on your calculator, I could do on mine. Also, I think there's an app. I think there's an app you could use too for the TI-80, whatever, 3 or 4.
to do what? To kind of broadcast it?
Yeah. I mean,
Um,
I don't know. It's
yeah,
just-
I mean, I don't know.
I think the confusing part about it is because usually I'm used to like the calculator being able to put in like fractions,
Yeah,
and then on this one you can only do it like dividing. You get me? It kind of throws me off a bit.
so what kind of calculators you all have? Like, you have like, TI-84s, right?
Yeah, no, it's just kind of like being used to older like calculators at my school would be able to just put in fractions.
Yeah, you could put a
So-
fraction in this,
You can how?
just 13 divided by 54.
Oh, I know that. It's just the visual, it kind of throws me off because it's more long in the way it shows.
Uh,
Well, why don't I show you how I did it? I'll try to hold up my calculator every step of the way. Here, let me unshare this screen. Because what I do see, unshare this screen. What I do see people do a lot, which I think is not the best way to do these types of problems, is to do the entire calculation at once. Yeah, Anahi, do you have a question?
Yeah, I did. So is it possible to still get the right answer if we use like the actual 0.11393 that like the calculator gets instead of simplifying it? Because my interval is like slightly different.
Then mine?
It's like really similar, but since I use the whole big number, it's just like a few digits off.
Okay, so
Like,
well, that's
it's-
interesting because let me stop you there for a second. Because on my calculator, I always use the whole number. So let me show you what I did, if that's okay, and then you'll tell me, if you did it differently. Is that okay?
Yeah.
Okay, so okay. So the first thing I have in that formula is 13 over 54. So I do 13 over 54 and I get a number. I stop. Agreed with me?
Yeah.
And then what do I do with that? I multiply it by 1 minus itself, right? So what I do is answer times 1 minus answer. Answer automatically recalls the number from the previous line, which in this case is my P1 hat, and I multiply it by 1 minus itself. And I enter, and then I divide that by N1 plus 2, which is 54. So now I have the first piece. Do we agree?
Yes.
Now the second one was 4 over 51, correct? So I do just straight up 4. Can you guys see this? It's like blurry in my, hold on. That help? I'll do 4 over 51.
Yeah, it's better. Sorry.
Okay, so 4 over 51. And then answer times in parentheses 1 minus answer and parentheses. So I will then multiply it by 1 minus itself. I'll then divide it by 51. So you see how I do everything one step at a time? I don't plug everything in once.
Yeah.
And now I'm gonna take that first one that I got, which was that one, and add it to that one. I go up to the two numbers that I want, and I hit enter on them, and it brings it down. And I add it, and that gives me 0.0048 yada yada yada, and then square root answer, and that gives me that.
Got it.
So rather than trying to use 1,000 parentheses and having everything work at once, I just do it one step at a time.
Because I just use 0.241 and 0.078, and then the whole like actual square rooted part, I just did like as one big equation, and then I just used that for the rest of the steps. Like I just again copy pasted like all the answers.
Gotcha.
So mine was like 0.04 06 and 0.2759. So it was just like a little off.
So yeah, so that's probably not the biggest deal in the world, but in general, keeping every decimal every step of the way will give you the most accurate answer possible. And that's what that's what I do. I never approximate. Even if I only write a couple decimals down on paper, when it comes to actually doing the work, I keep everything. Starbucks Wi-Fi. What?
It's a joke.
Oh, sorry, I left. My internet went out. Well,
Starbucks
welcome back.
Wi-Fi sucks, that's why.
I see. I
it was
see.
a very inside bad joke. Okay.
Understood. I'll allow it. Now, for now, let's use the calculator. Let's go to stat. Tests. Let's go down to the 2 proportion Z interval. What is my X1 going to be?
It'd be 13,
It'll be 13. What's my N1?
54,
What's my X2?
4,
And what is my N2?
51.
What's my confidence?
Was it 90?
Yep. So what does the calculator tell me as my Z proportion, 2 proportion Z interval?
It says 0.04833 and then 0.27629.
So essentially what I got down there. Right?
Yes.
So which is easier, doing it by hand or doing it on the calculator?
Calculated.
Yes, that's why we have them. And you certainly, on your exams and your final, you want to know how to use them on the calculator, because who really wants to do these by hand? That's right, nobody. Okay. So that takes care of the first half of today. Can I do the calculator part? Yeah, go to second stat, go to stat tests, and then roll down to the 2 proportion Z interval.
Okay.
Now, what are we putting as our X's and our N's?
Well, the ends are the end values, right?
Not exactly, because this is a small sample, we have to adjust them. The N's are going to be your N plus 2s. Right? For the small sample confidence interval, we don't put in the actual values. We put in the adjusted values.
Oh, so 54.
54 will be N1.
And then 51.
And 51 will be N2. And what's my X1 and my X2?
X1, 13.
Good. X1 is 13. How about X2?
4.
And X2 is 4.
But 4 is still less than 10.
Yes, that's okay, because this is a small sample. I don't need it to be greater than 10.
But doesn't it have to be greater than 5?
No, just the 2 samples have to be bigger than 5.
Like combined?
Each sample must be bigger than 5, not successes and failures. The samples
just
must
the
be bigger than
same.
or equal to 5.
Okay, got it. I need a second. Okay, and then 90%?
90%.
Oh yeah, it's the same. Okay.
It's the same, right? So much faster, much easier. Everyone's happy. So now we did the confidence intervals, small sample and large sample. By the way, that makes 4 confidence intervals we have right now. And if you have your book, if you actually have the hard copy of the book, on the inside front cover is 8 scenarios for hypothesis tests and for confidence intervals, and we've done 4 of them, 4 confidence intervals so far. So in terms of confidence intervals, we're basically halfway done. Now we got to do the hypothesis tests for 2 proportions. Once we get past the proportions, then we go to the other half, which is means, averages. Everything we've done so far is proportions. But proportions are only half of what we really care about in this class. The other half is being averages. What's the average height, the average weight, the average this, the average that? Those aren't proportions. Those are legitimate averages, and we want them too. So for now, let's go to hypothesis testing. Hypothesis testing for 2 proportions. In this class, the null hypothesis is always going to be that P1 is equal to P2. Doesn't have to be that way in general, but the mathematics for when it's not is a little bit different, a little bit more complicated, so we're not going to worry about that. In this class, the null hypothesis for hypothesis testing about 2 proportions is always that they are equal, and therefore that their difference is 0. That's really what we're going to be caring about. What is their difference? So what are the 3 possible alternatives? If P1 minus P2 is not 0, what are the 3 possibilities?
P1 is greater than P2.
Okay, so P1 minus P2 is greater than 0.
P1 minus P2 is less than 0.
P1 minus P2 is less than 0.
And it does not equal 0.
And does not equal 0. So same idea in theory as 1 proportion. We have the 2 proportion situation. And again, we have our cutoff values. These are the cutoff values. And if we land beyond the cutoff values, then we reject the null hypothesis. If we do not land beyond the cutoff values, then we do reject the null hypothesis. Or yeah, so what is the p-value? The p-value equals the probability that, what's the wording that I used for the last one? The probability of being passed, z equals plus or minus. So now what is the z value? Well, it's going to be p1 hat minus p2 hat minus p1 minus p2, the true value. Of course, the true value under the null hypothesis, since we don't really know the true value, the best we can say is it's what the null hypothesis claims is the true value. And what does the null hypothesis claim is the true value of P1 minus P2?
0.
0. So this is actually 0 and doesn't play a role in the formula. Divided by the square root, and we already know this. Well, we think we know it. We would think, so I'm going to hold off there for a second. We might think that the radicand should be P1 hat 1 minus P1 hat over N1 plus P2 hat 1 minus P2 hat over N2. Like if you look back here to the confidence intervals, right? What was my denominator? The square root of P1 minus P over N, which is exactly the same thing as I had in my confidence interval. It was exactly the same. But there's something we have here that we didn't have in the other examples. And that's the idea that according to the null hypothesis, P1 and P2 are really the same. And if P1 and P2 are really the same, then we want to utilize that fact in the formula, and we do. What we do is we actually don't consider P1 or the first sample and the second sample separately. We pool the results together. We define P hats, not P1 hat or P2 hat, but P hats to be the total number of successes divided by the total number that we are sampling between the two groups. It's called the pooled proportion. Since we're working under the assumption that P1 hat and P2 hat are together, we actually pool the results. And what we do put in here is P hats 1 minus P hats over 1 over N1 plus 1 over N2. But no. Define this and use that and use P hat in the actual formula. But even if you don't really understand why, and again, I wasn't extremely rigorous because the math is requires calculus and beyond. Nevertheless, the formula still holds. We can still use the formula even if we don't know why, because we get a formula sheet, we get our notes, we can write this down, and we can even use a calculator and just plug it in. Okay, so for these results, we're going to pool the results and plug that in there. And if we're past the z that z value, we either reject the null hypothesis, or the p value is the probability of being past that. If it's less than alpha, less than the level of significance, we reject the null hypothesis. And if it's not less than the level of significance, then we do not reject the null hypothesis, the same way we did it before. How do we illustrate this the best way? Via an example. So let's just do a few examples of hypothesis testing. Let's take a look. Okay, this is a good one. I would like this one. False memories. There's a picture here of George W. Bush. And it says that while New Orleans lied underwater in the wake of Hurricane Katrina, President Bush was with Roger Clemens, the pitcher, at his ranch in Texas. That's the picture. That's what the caption claims. So the political event depicted in the picture was remembered by 31% of those surveyed. It was legitimately remembered by 31% of those surveyed, despite the fact that it never actually happened. In 2010, Slate, a current affairs and cultural magazine, surveyed over 5,000 readers regarding their perspective on several past political events and their memories of these events. Unbeknownst, the Mandela effect, yes. Unbeknownst to those surveyed, one of the events shown to each participant was fabricated, making this the largest false memory study conducted to date. The hypothesis of interest was whether political preferences guided the formation of false memories, as false memories have been shown to be more easily implanted in memory when they are congruent with a person's pre-existing attitudes. The figure was viewed by 616 participants. So 616 participants. I don't know what this is yet. I'm just going to call it N. Who categorize themselves as progressive. Okay, that's my first sample. 616 progressives. And 49 participants who categorize themselves as conservative. So N2 equals 49 conservatives. Now, I was having a political discussion before class started with someone, and I mentioned that I'm very much not interested in politics. It's not my thing at all. So I really don't even know the difference between a conservative and a progressive. I assume these are the Republicans and these are the Democrats. Does that make sense?
No.
Did I get it backwards?
Yeah.
Okay, so progressives are the Democrats and the conservatives are the Republicans. Okay.
Yes.
I mean, I seriously, politics is the least interesting thing in my life. So I apologize to those of you who are very passionate about it. It's not my thing. Anyways, the event was falsely remembered as having occurred by 212 of the progressives. So we have 212 successes here and 7 of the conservatives, 7 of those there. How strong is the evidence that a larger proportion of progressives have a false memory of this event than conservatives? So we're curious, how strong is the evidence that's not it. How strong is the evidence that a larger proportion of progressives, I'm gonna write Dems, have a false memory of this event than conservatives? Okay, so if progressives did not have a if a larger proportion of Democrats did not have a false memory of this event, what would the null hypothesis be? We're trying to test something. So what would the null hypothesis be?
Wait, if they did not?
Well, the question is,
0.
how strong is the evidence that they did, that the Dems have a larger proportion than the conservatives?
Oh, P1 is greater than P2?
Well, that's what we're trying to test, right? We're trying to test if P1 is greater than P2.
Oh, is the null hypothesis P1 is equal to P2?
Null hypothesis always gets the equal sign. Right? The null hypothesis always gets the equal sign. So the null hypothesis is that the difference is 0. And the alternative is that P1 is greater than, that P1 minus P2 is greater than 0. With me so far?
Yes.
Which means that we are looking for a value on the right side. So let's calculate our Z value. Let's calculate our Z based upon that formula that I have at the top. First of all, is it going to be plus or minus? We're on the right side. Is it plus or minus?
Plus.
Plus. It's the positive version because we're on the right side. So what is P1 hat minus P2 hat? So let's write the fraction out. What is P1 hat?
It'd be 212 divided by 616.
212 divided by 616. What is P2 hat?
Be 7 divided by 49.
49, 7 divided by 49 over the square root of, what is P hat?
It'd be both of them added together. So it'd be
Well, it's not the fractions added together. It's the numerators added together divided by the denominators added together. The total number of successes divided by the total number of
so it'd be 219.
219.
665.
665 times 1 minus that same number times 1 over N1. What's N1?
616.
616 plus 1 over N2. What's N2?
49.
49. All right, now,
Professor, so it doesn't matter that their samples are
small,
yeah,
No.
like one side.
doesn't matter. Does not matter. At least the book doesn't stress that. Only for confidence intervals. Okay, so let's see who can do this quicker, me or you guys.
You.
Wow, that's defeatist, isn't it? Got it. I think I got it. Maybe I made a mistake. I'm gonna wait for you guys to get your answer.
I think I got 3.76337.
I did not get that. I got 2 point something.
Okay.
I got 2 point something. Just try the math again. Because it's important to make sure we get these things right.
2.8857.
Yeah, that's what I got. 2.8857. Now, actually, I'm going to write out the whole thing because I'm going to use this in my calculator. 2.8856966849. And now, what's the probability of being past that? What's my p-value?
One second.
I'm teaching.
Okay. So,
So I'm leaving. I gotta go tutor for an hour,
oh, may I come back?
maybe.
All right. Okay, yeah.
Okay. All right, so what do we all get the same thing? What's the p-value? Anyone? Once I have the z-score, how do I find the p-value?
You put it in for
I don't know.
normal CDF.
I love it. I don't know. Okay, good.
Normal CDF.
Normal CDF. Normal CDF, and then what?
You would put that as your lower.
Put that in my lower, because I'm going to the right of it,
And then
or
you
my upper.
try putting as many nines as possible.
Sure, I put like 5 or 6 nines. I think once you hit like 2 nines, you're probably safe, but just in case I throw a bunch. And then,
You just you put I think the mean at 0 and the standard deviation at 1.
yep, 0, 1, always for Z's. And what does it give you? I know what mine gave me. What does yours give you?
Point 0.00195.
0.00195. Is that a likely event or an unlikely event?
Unlikely.
Unlikely. Is that less than 10%?
Yes.
Less than 1%?
Yes.
Is it almost as small as a tenth of a percent?
Yes.
That's a pretty unlikely event, correct?
Yes.
But yet it's predicated upon the null hypothesis being correct. So if I got something that unlikely under the assumptions that the null hypothesis is correct, what's a pretty good conclusion to make?
That there was a effect based on the bias of the voter, or
Well, but I'm saying let's keep it generic for a second and then we'll go to the context. I'm not saying you're wrong, but let's keep it generic for a second. If I got a result this unlikely under the assumption that the null hypothesis is correct, my conclusion is probably to do what generically?
to believe the alternative hypothesis.
Exactly, to reject the null hypothesis in favor of the alternative. And therefore, in this context, what can I conclude? Or what should I conclude?
That there is a bias when it comes to memories.
Yes, apparently that a larger proportion of Democrats have a false memory of this event than conservatives. Now, again, I don't know anything about politics, so this will be very silly to some of you, and you might even look at me with disdain and contempt more than you already do. But was Bush a Democrat or a Republican?
Republican.
Okay, so that means that it seems like this is a bad thing, and therefore Democrats would remember this is bad more than Republicans. So it all makes sense in my head then. Okay.
Yeah.
Okay. Does that make sense then? This overall problem.
Yeah, it made sense.
Okay. While we're here, just for fun, let's do a confidence interval and see if the confidence interval supports this this conclusion. Okay, let's go with confidence interval. So let's go to stat tests, two proportion z interval. And what would I plug in everywhere? Where's my data? Of course, we got to be a little careful here because I'd have to use the small sample confidence interval.
So we're using like 219.
So for X1, it's going to be 213. I take 212 and I add 1.
Okay.
For N1, it's going to be what number?
8.
618.
Oh, wait.
N1 is going to be 618. X2 is going to be what number?
8. Yeah.
8. And N2 is going to be what number?
51.
51. And then the question is what confidence to use. So since we're not given a confidence, let's start with 95% confidence. And what is your conclusion based upon 95% confidence?
95, you said?
Yeah, that was good to start with 95%. It's a standard cutoff, standard value, without any reason to do otherwise.
So like the value would be 0.08119, and then the second one would be 0.294441.
And what is not in that confidence interval?
0.
0. Which means I am 95% confident that the true difference in proportions is between 8% and 29.5%, i.e. a bigger than 0 difference, which means I'm going to conclude the same result that I had before. Does that make sense?
Yes.
Any questions on the two proportion confidence intervals or the two proportion hypothesis tests?
No.
Once you understand the concepts of confidence intervals and hypothesis testing, essentially the details might be different from case to case, but the idea is the same for all of them. Based upon what you have, you just get a range of values, the confidence intervals, or you perform a test, and you make your conclusion from that.
Wait, did we plug this into the calculator? Like, is there actual way to plug it in the calculator for this one?
Oh, you mean the test? Yeah, let's do that too. I completely forgot. We didn't do it the test with, yeah, let's do the test. We didn't do any tests in the calculator. So let's go back to the calc. To stat tests. Which one do you think we're gonna do for the two proportion test?
6.
6, what's it called? I already hit the button, so I forgot what 6 is. Is it the two? Z
Two
test?
prop Z test.
Yes, two prop Z test. And we're gonna put in the actual values here. So 212, 616, 7, 49. This is a P1 greater than P2 situation. So we calculate. And what's our Z score? What's our P value?
You want what answer do you want?
I want to know,
The Z.
what's the Z score and what's the P value?
The Z is 2.8856.
You mean the same one we had before?
Yes.
Oh my God, how about the P value?
The p-value is 0.00195.
OMG, that's the same one also.
Crazy, huh?
Mind blown. And so much easier on the calculator, isn't it?
Yes.
Yes.
This is why we do it.
What number did you put for the sea level?
No C level for a two prop Z test.
Oh, thanks.
All right, confidence intervals have confidence levels, but not as fun. I don't know about that. I don't know. I mean, there's something to be said for. Okay, never mind that. Shut down. All right. I guess I was wrong on the heat. I apologize.
My bad.
It's okay. No, it's I love you being forceful and you have strong belief in your opinion. I think it's fantastic.
Yes.
Yes. Okay. Meanwhile, are there any remaining questions?
How many of these have we?
Sorry, I didn't get two at once. Alberto, what was that?
How many of the prop tests have we learned?
Let's see. We did one. I think only two so far. One proportion and two proportion. Prop tests. I don't think prop tests have a small and large version. Only confidence intervals do.
Okay then.
Yeah. So we had the one proportion, the two proportion hypothesis tests, and the one proportion and two proportion small sample and large sample confidence intervals. Anahit, question.
Yeah, but I think there was someone else before me who wanted to ask something.
Who? Oh, that's right. Somebody else. And okay. Anyone else have a question? Someone was speaking a couple seconds ago. Anyone?
Okay, I'll just ask mine then. So how is the percentage so small if like the data supports the answer? Okay, there you go.
No, the data supports the null hypothesis being wrong.
But if it's like, let's say 1 and 2, I mean like 1 and 3 progressives, but 1 and 7 conservatives, how is that?
Yeah, so when you say the proportion of progressives is more than the proportion of conservatives,
Well, isn't that what we said?
but the null hypothesis said they were equal. Right? The null hypothesis is that they're equal. It's the alternative that's claiming the first is bigger than the second.
But I mean, but the answer said that like, could you assume that?
The answer said how strong is the
I mean,
evidence?
the question, my bad.
Yeah, so the question was how strong is the evidence that a larger proportion of the Democrats have a false memory of this event than conservatives? The null hypothesis is saying status quo, everyone's the same, everyone's equal, there's no difference, they're equal to each other. The alternative is, wait, no, I think we should test this. I believe that progressives have a larger proportion of progressives than Democrats, or than conservatives. So we perform the test, and we get a result of a p-value that is less than 0.2%. This is the likelihood the null hypothesis is correct based upon our results. Right? That's a very small chance that the null hypothesis is correct. Right?
Yes.
So I can't say it's wrong. Statistics can't claim blanket statements about whether one thing is right or not, but the evidence really suggests that we should reject what the null hypothesis is claiming in favor of the alternative.
Okay, makes sense.
Right? Small p-values mean small chance of getting this result if the null hypothesis were true. Therefore, reject the null hypothesis.
In the test, we have to make sure to say reject, right? Don't say it's wrong.
Don't say accept anything. We either reject the null hypothesis or we do not reject the null hypothesis.
Okay.
Right? Think of it like courts. Nobody's innocent in America. Either you're guilty or you're not guilty. And they can't even say that. We find the defendant not guilty. In other words, I'm not claiming they're innocent, but I couldn't find them. I'm sorry, I couldn't find them guilty. Maybe they are, maybe they're not. I couldn't find them guilty. Guilty until proven innocent. That's America. Well, okay. I said I wasn't going to talk politics, so take that back. I just pretend it never happened.
What do you mean it's the American dream?
Yes.
Yeah.
The American dream. Yes. Oh, living in America is great. That's all I'm going to say. Living in America is great. For those who are fortunate to be able to be in a position to take advantage of all it has to offer, which unfortunately is not everyone. Anywho, are there any other questions? I shouldn't talk about my opinions about different things. I'm here to teach statistics and do the best job I can.
Let's hear your opinion on the Lakers.
Okay, well, that's a good question. I mean, LeBron by himself can carry a team to the playoffs. I think that the supporting cast needs time to really figure out how to work together. I see them making it deep into the playoffs. I don't know if they're gonna. I don't think they have it to win it, but I certainly see them getting further than they did last year. Does that?
I think Russell Westbrook was a bad fit.
I don't know. When LeBron's out, he shines. I mean, he had that 35-point game or something a couple of games ago. I mean, he had a triple-double the other night. I mean, he certainly has what to offer. It's just a matter of, making work at the right time. Anyways, I don't want to keep people here if they don't care about basketball. If there's no other questions, we can stop for today, and I will see you guys on Thursday.